Hello, hello. Here is the first video in a series of 3 going over the Pre-Calculus Semester 1 Final Exam Review Packet. So your review packet is broken up into 3 units. Unit 1 is functions, Unit 2 is rational functions, and Unit 3 is logarithmic and exponential functions, and each one is going to have its own video. So let's go ahead and get started with the first question. It says, identify the following characteristics given the graph below. So the first thing we want to do is we want to find the domain. The domain is what is happening to your graph horizontally. So really I can see that this graph is going to continue going to the left and it's going to continue going to the right. So I just want to see everything in between to see if it exists. Right here we see that there is a break in continuity. Same thing right here as well. But we do have some closed circles, which means at -2 and +2, the function does exist. So that means for this particular curve, my domain is going to be all real numbers, which we can write as -infinity to infinity. For my range, I want to see what is happening vertically. So vertically, going bottom to the top, I can see that again, there is this break right here and right here. But again, horizontally, I can see that my graph exists everywhere as I move from the bottom to the top. So that means my range is also -infinity to infinity. Okay. Now, for intervals of increasing, what I want to do is I want to travel along my graph. So if I look at my graph, anytime my graph is going down, that is an interval of decreasing. So from here to here, in the blue, that is decreasing. And then I switch to increasing. And then it switches back to decreasing. And then switches to increasing because I'm going up, and then finally back to decreasing because my function is going down. So I want to go ahead and write out my different intervals for both of those scenarios. So increasing is what I had in pink, and that goes from -3 to -2. That's the first portion in pink. And then the second portion in pink goes from +2 to 3. And then for decreasing, that's what I highlighted in blue. The first interval from left to right is -infinity up to -3. I also have from -2 to 2. And I have 3 to infinity because it's going to keep going to the right. And it's going to keep decreasing as we move to the right. Okay. Next thing is maximum and minimum values. So your minimum, let's go ahead and jump all over the place. So your minimum is this point right here because it's at the bottom of your parabolic curve. And your maximum is this point right here, which is at the top of a parabola. So for the minimum, I can write that as an ordered pair. That's -3, 0. And my maximum is at 3, -1. Now, depending on the question, you may be asked to write it as an ordered pair, in which these two ordered pairs are perfectly fine, or they might ask you for the actual value. So if I were to ask you for the maximum value, I would say the maximum value is -1, and that is at x equals 3. So anytime I'm asking for the value, essentially I'm just asking for that y coordinate. Same thing for the minimum value, that's going to be 0 at x equals -3. All right, concavity. So concavity, again, you're going to be traveling along your graph. Concavity deals with your curves. Okay, so if you're, for something to be concave up, essentially your curve needs to be going in this direction, and for something that's concave down, it needs to be going in this direction, or it could be going in that direction as well. So pieces that are concave up, I'm going to go ahead and highlight in pink. That's this. That's concave up. And then in blue, I'll do concave down. That's this piece right here. So my interval for concave up is going to go from negative infinity to -2. And my interval for concave down is going to go from 2 to infinity. The tricky thing is when it switches from concave up to concave down. That's kind of hard to identify, but you'll see that with the next graph once we get to number 2. Your x-intercepts are wherever they cross or touch the x-axis. So we have this one right here at -3, 0, and that one right there at 1, 0. So I can go ahead and write those as ordered pairs. So -3, 0 and 1, 0. Your y-intercept is where it crosses the y-axis, and that's at 0, 1. And for the end behavior, you just need to see what's happening at your ends. So as x approaches positive infinity is to the right, negative infinity is to the left. So as x approaches positive infinity, I can see that this end is going down towards negative infinity. And as x approaches negative infinity, I can see that this end is going up towards positive infinity. So there is your end behavior. All right, number 2. So number 2, be very careful as you're writing your answers because as you can see, we've got all these crazy decimals. So kind of bear with me as we go through it. For your domain, again, I want to see what's happening as I move from left to right. This graph is going to keep going up and to the left, and it's going to keep going down and to the right. So my domain is going to be all real numbers, so negative infinity to infinity. And it's going to keep going up and down in both directions, so my range is also negative infinity to infinity. Now again, I'm going to go ahead and travel along my graph to see where I'm increasing or decreasing. So going from left to right, as I travel, I'm going down, so that's decreasing. And then at this point, it switches from decreasing to increasing. At this point, switches from increasing to decreasing. At this point, switches from decreasing to increasing. And then finally, back to decreasing. Okay, so let's go ahead and write all of those intervals. So increasing is what I have in pink, and that was -3.243 to -0.666. Also the interval from 2.038 to 4.271. Now there is a little U in between these two intervals, but I have run out of space because those decimals are kind of outrageous. Okay, this is going to be trickier for decreasing because there's actually 3 intervals. So I'm going to see if I can squeeze it on the line. So my first interval goes from negative infinity to -3.243. So negative infinity to -3.243. That's the first interval in blue. And then -0.666 to 2.038. And the last one goes from 4.271 to infinity. All right. I'm going to go ahead and erase a little bit so we can use the rest of the graph to answer the other questions. Okay, maximum values, those are going to be at your top humps. minimum values are going to be at the bottom. So again, you can write this one of two ways. You can write it as ordered pairs, but again, it depends on how the question is worded. So if it's just asking for the maximums, you can go ahead and write them as ordered pairs. If they're asking for the values, I would recommend writing them as your y value at your particular x value. So for example, my first maximum is at 6.413 at x equals negative 0.666. I also have one at 6.55, and that is when x equals 4.271. And then for my minimum, for my minimum, I have a minimum value of negative 8.561. And that was at an x value of negative 3.243. And then I also have another minimum value at negative 3.005 at x equals 2.038. You could also write those as ordered pairs. Okay, now for concavity. So let's travel along the graph. So over here, this piece right here is concave up. And then right about here, it switches to concave down. And then right about here, it switches back to concave up. And right about there, it switches to concave down. And it keeps going. So once again, when things are concave up, almost looks like a parabola opening up, and concave down would be similar to a parabola opening down. So you can kind of see how it shifts at your x-intercepts. So when I'm setting up my intervals, I'll go ahead and break them apart at those particular values. So my concave up, my first interval for concave up goes from negative infinity to negative 2. And I also have from 1 to 3. And then for my concave down, I have from negative 2 to 1 and 3 to infinity. Okay. My x-intercepts are where they cross the x-axis or touch the x-axis. So I have 1, 2, 3, 4, 5. That's a lot of x-intercepts. But I have one at negative 4, 0, negative 2, 0, 1, 0, 3, 0, and 5, 0. Okay, y-intercept, we just have that 1 right here at 5, so that would be 0, 5. And then for my ends, as my graph moves towards positive infinity on my x, I can see my end is pointing down towards negative infinity. And as my graph moves towards negative infinity for my x, I can see that my graph is going up towards positive infinity. All right, moving on from characteristics. Finding the domain of the following functions, write your answers in interval notation. So really, when you're trying to find the domain, there's a couple of things that you have to pay attention to. Number one, you cannot take the square roots of negative numbers because they are imaginary. And number two, you cannot divide by 0 because that doesn't give you a real number for an answer. So for number 3, I see that I have a radical, and so what's inside my radical, this 3x minus 2, has to be positive. So that means it can be greater than or equal to 0, because you can actually take the square root of 0. So I'm going to go ahead and solve this inequality. I'm going to add 2 to both sides and divide by 3, so I get x is greater than or equal to 2/3. The question does ask you to write it in interval notation, so that means if I were to graph this on a number line, greater than or equal to 2/3 would be everything to the right. So when I were to write that as an interval, it would be 2/3 to infinity. Number 4 is kind of a double whammy because it is a rational with a radical. So there's a couple of things that you need to pay attention to. First of all, my square root has to be greater than or equal to 0. So x minus 7 is greater than or equal to 0, and it's okay for that one to equal 0 because it's in the numerator. So I can add 7 to both sides, and I get x is greater than or equal to 7. I also have my denominator that I have to worry about. So for my denominator, x minus 10 cannot equal 0. So that means x cannot be 10. So what's happening here is I will have all of my numbers that are greater than 7, but I cannot equal 10. So that creates a break in my interval. So when I'm writing that in interval notation, I am going from 7 to 10 with a break, and then 10 to infinity. So since x cannot be 10, we do have to break up that interval from 7 to infinity by excluding that 10. And that's to incorporate your parentheses with the union in between. Okay. Number 5. So number 5, I'm going to worry about this denominator. Again, your denominator cannot be 0, but also since you do have a radical, underneath the radical has to be positive. So since this can't be 0, I'm going to take what's underneath my radical, and that's just going to be greater than 0 instead of greater than or equal to. So this becomes x is greater than 3, so that as an interval goes from 3 to infinity. Now, if you noticed, I completely ignored my numerator. And the reason why I ignored this numerator is because it is a quadratic, and quadratics do not give us issues with domain. The domain for a quadratic is all real numbers. So really, the only thing you need to worry about is this radical and your denominator not being 0. Okay. Number 6, similar to number 4, I need to have my radical being positive or equal to 0. So I have 2x plus 4 is greater than or equal to 0. So I'm going to subtract 4 from both sides and divide by 2. So I get x is greater than or equal to negative 2. And I also have that information that x minus 5 cannot be 0 since I can't divide by 0. So that means x also cannot be 5. So once again, we do have this break in our domain. So it's everything greater than negative 2. So it's everything to the right. However, you can't actually equal 5 because you can't have 0 in the denominator. So it creates a break in your domain once again. So I'm going from negative 2 to 5. And then 5 to infinity. All right. Number 7. So 7 starts to take us into transformations of functions. So the dotted curve represents f of x. Express the solid line g of x as a transformation of f of x. So really what I want to see is I want to see how this red curve turned into this black curve. And what I noticed right away is that a reflection happened. So it was a reflection over the y-axis. And anytime I'm writing an equation with a reflection over the y-axis, what that means is that my negative was inside my function. So my negative is going to be inside my parentheses with the x. If you look at number 8 has a negative in front. The negative in the front means you're going to have a reflection over the x-axis. So it all depends on where your negative is. I'm going to go ahead and continue with number 8 and list out my transformations. So I have a reflection over the x-axis. I also am moving to the left 1. That's this plus 1 over here that tells me I'm moving to the left. And I'm also going to be moving up 2. Now what I like to do is I like to create a table and then manipulate the table based off of my transformations. So I'm going to go ahead and take all of my original ordered pairs. So my first point is at negative 2, 4. And then I have 0, 1, 1, 2, 2, 1, and 3, negative 2. And what I want to do is I want to take all of these points, those are these points over here, those are the ones that I just took for the table, and then I want to transform them based off of the transformations that I have listed. So if I am reflecting over the x-axis, so let's say going from here to here, what that does is that affects my y values. Moving up 2 will also affect my y values. So essentially for the reflection, I'm going to take all my y values and multiply them by negative 1. And then I want to take those points and move them up 2 units. Similarly for my x, since I need to move to the left, I'm going to take all of these x coordinates and I'm going to subtract 1 since I need to move to the left. So for my x's, I'm going to subtract all of these x's by 1. So that gives me negative 3, negative 1, 0, 1, and 2. And then for my y's, I'm going to start by multiplying by negative 1 and then adding 2. So that's negative 4 plus 2, negative 1 plus 2, negative 2 plus 2, negative 1 plus 2, and then finally this becomes positive 2 plus 2, and there's your last point. So then I can go ahead and take these points and plot them and then see how my red curve has transformed into this purple one. So let's see, negative 3, negative 2 is right here, negative 1, 1, 0, 0, 1, 1, and 2, 4. So what happened here is I have this curve right here, and then it continues over here. So I can see that there was a reflection because now it's upside down. I can also see that the graph has shifted to the left 1 unit and up 2 units after the reflection. Whoops. Okay. Number 10 is just identifying all of the transformations. So again, I do have this negative in the front, so that is a reflection over the x-axis. I do have a 2 in the front, so that becomes a vertical stretch of 2. And let's see, inside my function, I have minus 1, so that's the right 1. And up 1 is that plus 1 on the outside. For number 11, this 1/2 in the front is a vertical compression or a vertical shrink. Both of those mean the same thing, so a vertical shrink of 1/2. And that minus 3 on the inside means I move to the right 3 units. Okay. Number 12. So number 12, you have these 2 graphs that have already been transformed, and what we want to do is we want to write the original, or we want to write the equation that matches the new graph. So one thing you need to do is you really need to understand what your parent functions look like. So for this first graph for number 12, this is actually going to be a transformed square root graph. So the first thing I'm going to do is I'm actually going to plot my original square root curve and then see how I can manipulate this blue curve into the black one over here. So I can see that it is going, it's upside down. So essentially I have this reflection over my x-axis, but it has also been reflected over my y-axis. So now I'm heading in that direction. And then from there, I also have a vertical shift of moving up 4 units. So let me go ahead and list all of that together. So the first thing I did was I reflected over the x-axis. I also reflected over the y-axis, and we also moved up 4 units. So since I have this double reflection going on, that means I'm going to have a negative in the front of my square root and a negative on the inside of my square root. And moving up 4 means I'm going to be adding 4 to the outside of my radical. For the second one, it is a quadratic. So let's go ahead and plot our original quadratic. And one thing I noticed right away is that it moved horizontally 2 units. So we'll say that that is to the right 2. And another thing I noticed is that your graph is a little wider than it originally was. So right here, if you notice, your original quadratic from here to here is 1 unit. However, from here to here, I have this vertical shrink. So instead of this being right here, 1 unit apart, instead it's half a unit vertically. So that means we had a vertical shrink. Whoops, shrink. Shrink of 1/2. So when I write that for my equation, it's f of x equals, I'm going to put my 1/2 in the front, and this is a quadratic, so I'm going to need something squared, and I move to the right 2, so that's going to be x minus 2. So my equation is 1/2 times x minus 2 squared. Okay, piecewise. So number 13, graph the piecewise function. So anytime I'm graphing a piecewise function, what I always want to do first is I want to set up my boundaries. And my boundaries come from these restrictions on my domain. So I have a boundary at 0. So that's my first one. And I also have a boundary at 2. And it's going to separate my graph into 3 sections. So the first one I'm going to graph is negative x plus 1, and that's when x is less than 0. So less than 0 is going to be everything to the left of this vertical dotted line. So it is a linear function, so that means I'm going to start at 1 on my y-axis. This is going to be an open circle because if I look at my inequality, it is when x is less than 0 and not or equal to. And then normally when I graph a line, I move to the right. So my slope is negative 1, so that means I would go down 1 over 1, down 1 over 1, but I'm going in the wrong direction. So I'm going to go ahead and fill in my line in the other side. And I'm going to erase this purple dot that I had right here. And here is the first piece of my graph. For my middle function, which I'll go ahead and do in pink, that is equal to 3. So that's going to be a horizontal line in between 0 and 2. So I'm going to go to 3 on my y-axis. I'm going to go ahead and draw my horizontal line. And when I hit that boundary of 0, it can equal 0 right here at my inequality. So I'm going to make this a closed circle. But right here, it cannot equal 2. So that means at that point, I'm going to make that an open circle. And then our last piece is a quadratic, and that has been shifted to the right 3 units. So normally your quadratic starts at the origin, but I'm going to move to the right 3 units, 1, 2, 3. So there's the vertex of my parabola, and since there is no vertical stretch or compression, that means I'm going up 1 over 1 in both directions. And this one is also a closed circle because of my inequality right there. So I can go ahead and draw my curve. So there is your graph. For number 14, it's going backwards. So this time I have my graph and I want to write out the piecewise function. One thing I notice right away is where my boundaries are. So it's where my graphs break. And so for my first graph, that is everything to the left of negative 1. So that is going to be for x is less than or equal to because of the closed circle. So I'm going to say x is less than or equal to negative 1. For my middle piece, that is going from negative 1 to 2, and I notice both of those have open circles at the ends. So I'm going to write negative 1 is less than x is less than 2. And then finally, for my last piece, that's from 2 to infinity. So I'm going to say x is greater than or equal to, because of this closed circle, 2. Now I need to write out my equations. So one thing I notice about my first piece that I'm going to do in purple is that it is a quadratic. I also notice that it is opened upside down. So that means I'm going to have a negative in front of my parentheses. My vertex has been shifted to the left 2 units. So I'm going to write this as x plus 2 squared. And it's also been shifted vertically 3 units. So that'd be plus 3 for my equation. For my middle piece that I'm going to do in blue, my middle piece is a linear function. So I can see where it crosses my y-axis. That's at 1. And my slope is 1 because I'm going up 1 over 1, up 1 over 1. So my equation is just x plus 1. And then for this last piece is an absolute value function. And I can see my vertex of my absolute value has been shifted to the right 3 and down 3. So I'm going to write this as absolute value of x minus 3 for it to move to the right, and then down 3. So I'm going to do minus 3 on the outside. Okay, so that's it for piecewise. What's next? Use the given functions to answer the following questions. Number 15, find h of x plus h. So whatever's in my parentheses, that is what I'm plugging in for x. So my h function is x squared minus 5. So I'm going to write this as x plus h squared minus 5. And then my job right here is to simplify it further. So I'm going to write this as x plus h times another x plus h minus 5. And this I just need to multiply out. So x times x is x squared. X times h is xh, which seems weird, but just go with it. H times x is also xh. And finally, h squared minus 5. These are like terms, so I can combine those two. So I have x squared plus xh plus another xh is 2xh plus h squared minus 5. And there's no other like terms that I can combine, so there is my final answer for number 15. So even though it does say x plus h, just work through it like you normally would if that h were a number. You're just going to have more variables in the end. 16 is a composition. So this is saying h of f of x. So what that means is I'm going to take h of f of x, which is 2x minus 3. So once again, what's in my parentheses, that is what I'm going to substitute for x into my h function, which is this one right here. So once again, I'm going to go ahead and rewrite this. This is 2x minus 3 times another 2x minus 3 minus this 5 over here. And I'm just going to work through that multiplication. So 2x times 2x is 4x squared. 2x times negative 3 is negative 6x. Negative 3 times 2x is negative 6x. Negative 3 times negative 3 is a positive 9 minus that 5. So combining like terms again, I have 4x squared minus 12x plus 4, since 9 minus 5 is 4. All right. Number 17 is also a composition, but this time we actually have a number to plug in. So the first thing I'm going to do is I'm actually going to find h of negative 2. So I'm going to take negative 2 and plug it into my h function. So I have negative 2 squared minus 5. That is 4 minus 5, which is negative 1. And now that becomes my input for my next function. So now I'm going to take k of negative 1. So I have negative 1 squared minus 2 over 3. Let's see, negative 1 squared is 1, minus 2 is negative 1 over 3. So negative 1/3. It's your final answer for that one. All right, next up, finding inverses. Okay, so to find the inverse of a function, your first step is to change your function notation into an equation. So I'm going to change my g of x to a y. So I'm going to write this as y equals square root of 3x plus 2 minus 4. Now, anytime you're talking about the inverse, you're always going to switch your x and y's. So now I'm going to rewrite this. I'll go ahead and change colors. I'm going to rewrite this as x equals square root of 3y plus 2 minus 4. And then from here, you are going to solve for y. So this is when your algebraic skills come in handy. So I'm going to go ahead and start by moving the 4. I'm going to add 4 to both sides. So I get x plus 4 equals square root of 3y plus 2. From here, to undo my square root, I'm going to square both sides. So that leaves me with x plus 4 squared equals 3y plus 2. I'm going to subtract 2 from both sides. So I have x plus 4 squared minus 2 equals 3y. And then finally, divide by 3. I am going to write this in function notation. So my final answer is g inverse of x equals this giant fraction. So x plus 4 squared minus 2 over 3. I'm going to do the same thing for 19. So again, I'm going to start by changing my f of x to a y. So I have 2 to the x minus 5 plus 1. And then I'm going to switch my x and a y. And then I'm going to go ahead and start solving for y. So this one we're dealing with an exponential. So I'm going to still start by subtracting 1 from both sides. So I have x minus 1 equals 2 to the y minus 5. Now, anytime you're solving for an exponent, that's when you're going to have to incorporate some logarithms here. So since I'm trying to get this y minus 5 out of being an exponent, that means I need to change it to logarithmic form. So as I write it in logarithmic form, this is going to be a log base 2 because your base for your exponential matches your logarithm. So this would be log base 2 of x minus 1 equals your exponent, which is y minus 5. And then from here, I can easily continue to solve for y. I can add 5 to both sides. So then I have log base 2 of x minus 1 plus 5 equals y, which I can go ahead and write in function notation. So I have f inverse of x equals log base 2 of x minus 1 plus 5. So the key for this one is remembering to change it to logarithmic form since it does end up being an exponential function. For number 20, given negative 3, 4 is a point on g of x, what point is on g inverse of x? This one's super simple. Just switch your x and your y coordinates, which is why when we're finding the inverse, we switch our x's and y's. All right, almost done. 2 more questions for unit 1. So what are the x-intercepts of the following function? X cubed plus 2x squared minus 24x. What you want to do is you want to factor it. So I notice that they have an x in common, so I can take out my x. So I have x times x squared plus 2x minus 24. And I want to find two numbers that multiply to negative 24 and add to 2. What is that? 6 and negative 4. So since I have 3 factors, that means I'm going to have 3 x-intercepts. So each factor is going to give me an x-intercept. For this first one, I get x equals 0. For the second one, I get x equals negative 6. And for my last factor, I get x equals 4. So that means my x-intercepts are at 0, 0, negative 6, 0, and 4, 0. All right, last one for this unit. Use the graph of the polynomial to write an equation in factored form. So in order to write the equation in factored form, we need to pay attention to where our x-intercepts are. So this one has 3 x-intercepts. So I'm going to go ahead and start by writing f of x equals a, which I'm going to have to figure out what that is in a second, and then I'm going to start to list out my factors. So since I have an x-intercept at -4, that comes from a factor of x plus 4. I have a factor at -3, or 0 at -3, so that factor is going to be x plus 3. And I also have an x-intercept at 2, so that's going to be x minus 2. Now, one thing you should notice is at this particular x-intercept, your graph bounces. It doesn't actually go through that x-intercept, it bounces. So what that means is that particular factor is going to have an even exponent, or in this case, a square. So now I need to figure out how I'm going to solve for a. So in order to solve for a, you can pick any point that's on your graph and use that to plug in the values to solve for a. I like to use my y-intercept because it's one of the easiest points to plug in. So I'm going to use the point 0, -6. So my y is -6, and I'm plugging in 0 for my x. And then I just need to simplify, so that gives me a times 4 times 3 times -2 squared is 4. Let's see, 4 times 3 is 12, times 4 is 48. And then I can divide both sides by 48. Don't forget to reduce. So I get a equals -1/8. So my final answer is going to have my a, which was -1/8, plus all of my factors. So x plus 4, x plus 3, and finally x minus 2 squared. All right, so that concludes the first video for your final exam review packet.